What if the universe held secrets so strange, so mind-bending, that even the brightest scientists are left scratching their heads? Picture this: a star dies, but instead of fading into darkness, it transforms into something so dense, so powerful, that a single teaspoon of it would weigh 1 billion tons. This isn't science fiction, it's the reality of neutron stars. These cosmic enigmas are the remnants of massive stars that have exploded in supernova, yet they refuse to go quietly. Instead, they become some of the most extreme and mysterious objects in the universe. Neutron stars are like the universe's ultimate puzzle boxes. They spin faster than a blender, have magnetic fields strong enough to rip atoms apart, and are so dense that they warp the very fabric of space and time around them. But here's the thing: despite decades of study, these bizarre objects are still shrouded in mystery. From unexplained bursts of energy to strange glitches in their rotation, neutron stars keep throwing curveballs at scientists. In this video, we're diving into 20 of the most baffling unsolved mysteries surrounding neutron stars. Why do some of them suddenly speed up? Could they be hiding exotic forms of matter that defy our understanding of physics? And what happens when two of these cosmic powerhouses collide? By the end of this journey, you'll not only get a glimpse into the weird and wonderful world of neutron stars, but also see why they're one of the most fascinating frontiers in modern science. So buckle up, because we're about to explore the universe's most extreme leftovers, and trust me, you won't want to miss a single second. Now, turning to the first mystery on our list, we encounter one of the most baffling phenomena in the cosmos: fast radio bursts, or FRB. Imagine a burst of energy so intense that it releases more power in a millisecond than the sun does in 80 years. These fleeting flashes of radio waves have puzzled scientists since their discovery, and neutron stars, especially magnetars, are prime suspects in this cosmic whodunit. Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, are thought to be the likely culprits behind these bursts. But here's the catch: no one knows exactly how they do it. Some theories suggest that FRBs could be caused by starquakes, massive shifts in the neutron star's crust that release enormous amounts of energy. Others propose that the bursts might result from magnetic field reconnections, where the star's magnetic lines snap and realign, unleashing a torrent of radio waves. Recent observations have added even more intrigue to the mystery. In 2020, astronomers detected an FRB originating from within our own galaxy, linked to a known magnetar. This discovery provided the strongest evidence yet that magnetars could be responsible for at least some of these bursts. However, not all FRBs fit this explanation, leaving scientists to wonder if there are multiple sources or mechanisms at play. The mystery of fast radio bursts is far from solved, but each new discovery brings us closer to understanding these enigmatic signals. Could they be the cosmic fingerprints of neutron stars in turmoil, or is there something even stranger at work? As we continue to unravel this puzzle, one thing is certain: the universe is full of surprises, and neutron stars are at the heart of some of its most profound mysteries. Now, shifting our gaze to another cosmic enigma, we delve into the peculiar phenomenon of pulsar glitches. Picture this: a neutron star, spinning with the precision of a cosmic clock, suddenly speeds up without warning. These sudden jumps in rotation, known as glitches, are one of the most puzzling behaviors observed in pulsars, and they offer a tantalizing glimpse into the inner workings of these dense stellar remnants. The leading theories to explain these glitches revolve around the complex dynamics within a neutron star. One idea suggests that starquakes, massive shifts in the star's rigid crust, could be the culprit. Just as tectonic plates on Earth can shift and cause earthquakes, the crust of a neutron star might crack under immense pressure, releasing energy that briefly speeds up its rotation. Another compelling theory points to the interaction between the star's superfluid core and its solid crust. Neutron stars are thought to have a core filled with superfluid neutrons which flow without friction. If this superfluid suddenly transfers angular momentum to the crust, it could cause the star to spin faster in a glitch. One of the most famous examples of a pulsar glitch occurred in the Vela pulsar, a neutron star located about 1,000 light-years from Earth. In 1969, astronomers observed a sudden increase in its rotation speed, followed by a gradual return to its normal spin rate. This event provided critical evidence for the superfluid theory, as the behavior matched predictions of how a superfluid core might behave. However, not all glitches follow this pattern, leaving scientists to wonder if multiple mechanisms are at play. The mystery of pulsar glitches is far from solved. Each glitch offers a unique opportunity to probe the extreme conditions inside neutron stars, but the exact processes driving these events remain elusive. Are they the result of starquakes, superfluid dynamics, or something even more exotic? As we continue to study these cosmic anomalies, one thing is clear: neutron stars are not just dense remnants of stellar explosions. They are dynamic, ever-changing objects that challenge our understanding of physics itself. Now turning to a concept that pushes the boundaries of our understanding, let's explore the intriguing possibility that some neutron stars might not be neutron stars at all, but something even more exotic. Enter the hypothetical quark star, a cosmic object that could rewrite the rules of particle physics and stellar evolution. Unlike neutron stars, which are made up of densely packed neutrons, quark stars are theorized to be composed of something far stranger: exotic matter made up of quarks, the fundamental building blocks of protons and neutrons. But not just any quarks. These stars might contain strange quarks, a rare and unstable form of matter that could exist only under the extreme pressures found in these stellar remnants. The idea of quark stars stems from the fact that neutron stars are already pushing the limits of how matter can behave. Under the crushing gravity of a neutron star, protons and electrons are forced together to form neutrons, creating a dense, neutron-rich core. But what if the pressure becomes so intense that even neutrons break down? This is where quark stars come into play. At these extreme densities, neutrons might dissolve into their constituent quarks, forming a quark-gluon plasma, a state of matter that hasn't existed freely since the earliest moments of the universe. If quark stars exist, they would represent a new phase of matter, one that could provide unprecedented insights into the fundamental forces of nature. Detecting quark stars, however, is no easy task. One of the biggest challenges is that they would look almost identical to neutron stars from a distance. Both would emit similar radiation, spin rapidly, and have comparable masses and sizes. The key difference lies in their internal structure, which is hidden from direct observation. Scientists rely on indirect clues, such as the cooling rates of these stars or the gravitational waves they produce during collisions, to distinguish quark stars from their neutron counterparts. Even then, the evidence remains inconclusive, leaving quark stars firmly in the realm of theory for now. The existence of quark stars would have profound implications for our understanding of the universe. Not only would they confirm the presence of strange quark matter, but they could also shed light on the behavior of matter under conditions so extreme that they cannot be replicated in any laboratory on Earth. This could revolutionize our understanding of particle physics, offering clues about the strong nuclear force that binds quarks together and the nature of matter itself. Additionally, quark stars could provide new insights into stellar evolution, revealing how the most massive stars transform into the densest objects in the cosmos. As we continue to probe the mysteries of neutron stars, the search for quark stars remains a tantalizing frontier. Are these exotic objects hiding in plain sight, masquerading as neutron stars, or are they purely theoretical constructs never to be observed? For now, the nature of quark stars remains one of the most captivating unsolved mysteries in astrophysics, a puzzle that challenges our understanding of the universe at its most fundamental level. Now shifting our gaze to another cosmic enigma, let's delve into the puzzling gap that exists between the heaviest neutron stars and the lightest black holes. This so-called mass gap has left scientists scratching their heads as it challenges our understanding of how massive stars end their lives and what happens in the moments just before they collapse into these extreme objects. Neutron stars, as we've discussed, are the dense remnants of massive stars that didn't quite have enough mass to become black holes. They typically weigh in at around 1.4 times the mass of our Sun, though some can reach up to 2.2 times that mass. Black holes, on the other hand, usually start at around 5 times the mass of the Sun. This leaves a curious gap between 2.2 and 5 solar masses, a range where very few objects have been observed. Why does this gap exist, and what does it tell us about the final moments of a star's life? One leading theory suggests that the physics of stellar collapse might be responsible. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, leaving behind either a neutron star or a black hole. But the exact outcome depends on the star's initial mass, its composition, and the dynamics of the explosion. It's possible that stars in the mass gap range simply don't produce stable remnant. Either they collapse directly into black holes without forming neutron stars, or the resulting neutron stars are unstable and quickly collapse further. Recent observations of gravitational waves have started to shed light on this mystery. In 2017, the detection of a neutron star merger by the LIGO and Virgo observatories revealed that the combined mass of the two stars was around 2.7 times that of the Sun, right in the middle of the mass gap. This event, known as GW 170817, produced a remnant that was either a heavy neutron star or a low-mass black hole, but its exact nature remains unclear. Such observations are helping scientists refine their models of stellar collapse and the formation of compact objects. The implications of solving this mystery are profound. Understanding the mass gap could reveal new details about the behavior of matter under extreme conditions, the limits of neutron star stability, and the processes that govern the birth of black holes. It could also help us piece together the life cycles of the most massive stars in the universe, from their fiery beginnings to their dramatic ends. As we continue to explore this cosmic puzzle, one thing is certain: the missing link between neutron stars and black holes is more than just a gap in our observations. It's a window into the fundamental forces that shape the universe. And with every new discovery, we come one step closer to unlocking its secrets. Now turning to one of the most extreme objects in the universe, let's explore the enigma of magnetars. These neutron stars are not just dense remnants of stellar explosions, they are cosmic powerhouses with magnetic fields so intense they defy imagination. To put it in perspective, a magnetar's magnetic field can be trillions of times stronger than Earth's. If a magnetar were located halfway between the Earth and the Moon, its magnetic field would erase the data on every credit card on our planet. That's the kind of power we're talking about, but how do these unimaginably strong magnetic fields form? The answer lies in the chaotic aftermath of a supernova. When a massive star collapses, its core spins rapidly, and its magnetic field becomes concentrated and amplified. In some cases, this process creates a magnetar, a neutron star with a magnetic field that's off the charts. These fields are so intense that they can twist the star's crust, causing starquakes that release bursts of energy in the form of X-rays and gamma rays. These outbursts are among the most energetic events in the universe, capable of releasing more energy in a fraction of a second than the Sun does in years. Studying magnetars, however, is no easy task. These objects are incredibly rare, with only about 30 confirmed magnetars known to exist in our galaxy. They are also highly unpredictable. A magnetar can remain quiet for years, only to suddenly unleash a massive burst of radiation without warning. This unpredictability makes them difficult to observe and even harder to study in detail. Scientists rely on a combination of X-ray and gamma-ray telescopes to catch these fleeting events, but even then, the data is often incomplete or difficult to interpret. One of the biggest challenges is understanding how magnetars maintain such extreme magnetic fields. Some theories suggest that the fields are generated by a dynamo effect in the star's interior, where swirling currents of charged particles create and sustain the magnetic field. Others propose that the fields are remnants of the original star's magnetic field, amplified during the supernova explosion, but without more observations, these ideas remain speculative. Despite the challenges, magnetars offer a unique window into the physics of extreme environments. Their intense magnetic fields and violent outbursts provide clues about the behavior of matter under conditions that cannot be replicated on Earth. By studying these cosmic oddities, scientists hope to uncover new insights into the nature of neutron stars, the limits of magnetic fields, and the processes that drive some of the most energetic events in the universe. As we continue to unravel the mysteries of magnetars, one thing is clear: these objects are not just fascinating curiosities, they are key to understanding the extremes of cosmic physics. And with every new observation, we come closer to unlocking the secrets of these magnetic marvels. Now, shifting our focus to another intriguing mystery, let's delve into the puzzle of neutron star cooling. These incredibly dense remnants of supernova are born scorching hot, with temperatures reaching hundreds of billions of degrees. But over time, they cool down, a process that, surprisingly, doesn't always follow the expected patterns. Understanding how neutron stars lose their heat is not just a question of curiosity. It's a key to unlocking the secrets of their interiors and the exotic physics at play. One of the primary ways neutron stars cool is through neutrino emissions. Neutrinos are ghostly particles that barely interact with matter, allowing them to escape the star's core and carry away energy. In some models, this process dominates the cooling in the first few thousand years of a neutron star's life. However, observations of some neutron stars show cooling rates that are much slower or faster than predicted, leaving scientists scratching their heads. Another factor that complicates the picture is superfluidity. Inside a neutron star, the core is thought to contain a superfluid, a state of matter where particles flow without friction. This superfluid can influence how heat is transported and lost, potentially slowing down or speeding up the cooling process. But the exact properties of this superfluid, such as its density and temperature dependence, remain poorly understood, making it difficult to predict how it affects cooling. Adding to the mystery are neutron stars that seem to defy expectations entirely. Take, for example, the neutron star Cassiopeia A, which has been cooling at an unexpectedly rapid rate. Some theories suggest this could be due to a phase transition in its core, where matter shifts into a new state, releasing energy and accelerating cooling. On the other hand, other neutron stars, like the one in the supernova remnant Hess J 1731-347, appear to be cooling much more slowly than models predict, hinting at processes we don't yet fully grasp. The challenge lies in reconciling these observations with theoretical models. Neutron stars are incredibly complex systems, with their interiors governed by extreme densities, temperatures, and magnetic fields. Even small changes in our understanding of the equation of state, the relationship between pressure, density, and temperature, can dramatically alter predictions about cooling rates. This makes neutron stars not just fascinating objects to study, but also natural laboratories for testing the limits of our knowledge about matter under extreme conditions. As we continue to observe and analyze these cosmic cooling puzzles, one thing is certain: neutron stars are far from simple. Their cooling behavior holds clues to the fundamental physics of their interiors, and every new discovery brings us closer to understanding the true nature of these enigmatic objects. With each observation, we peel back another layer of the mystery, revealing the intricate dance of heat, matter, and energy that defines the life of a neutron star. Now turning to the riddle of neutron star atmospheres, we find ourselves staring into one of the most perplexing layers of these cosmic enigmas. Unlike the familiar atmospheres of planets or even stars, neutron star atmospheres are a realm of extremes where the rules of physics as we know them are pushed to their limits. These thin outer layers are not just a shell, they are a window into the star's interior, offering clues about its composition, temperature, and magnetic fields. Yet, despite decades of study, the true nature of these atmospheres remains shrouded in mystery. One of the primary tools scientists use to study neutron star atmospheres is the observation of X-ray and ultraviolet emissions. These high-energy signals are emitted from the star's surface and can reveal details about its temperature and chemical makeup. For example, certain elements in the atmosphere, like hydrogen or helium, leave distinct fingerprints in the X-ray spectrum. By analyzing these patterns, researchers can infer what the atmosphere is made of and how it behaves. However, the data often doesn't match the predictions of existing models, leaving scientists puzzled. A major challenge lies in the extreme conditions found on neutron stars. Their surfaces are incredibly hot, with temperatures reaching millions of degrees, and their magnetic fields are trillions of times stronger than Earth. These factors can dramatically alter the behavior of atoms and molecules in the atmosphere, making it difficult to predict how they will interact with light. For instance, the intense magnetic fields can split energy levels in atoms, a phenomenon known as the Zeeman effect, which complicates the interpretation of spectral lines. This means that even if we detect certain elements, their signals might be distorted beyond recognition. Adding to the complexity is the possibility that neutron star atmospheres are not uniform. Some regions might be dominated by hydrogen, while others could contain heavier elements like carbon or iron. This patchwork of materials could explain why observations often show unexpected variations in brightness and spectral features. But without a clear understanding of how these elements are distributed or how they interact with the star's magnetic field, creating accurate models remains a daunting task. Another layer of the mystery involves the role of surface temperatures. Neutron stars cool over time, but the rate at which they do so can vary depending on the composition and structure of their atmospheres. For example, an atmosphere rich in heavy elements might trap heat more effectively, slowing down the cooling process. On the other hand, a lighter atmosphere could allow heat to escape more quickly. Understanding this relationship is crucial for piecing together the life cycle of neutron stars, but it's a puzzle that's far from solved. As we continue to probe the secrets of neutron star atmospheres, each new observation brings both answers and questions. The interplay of magnetic fields, surface temperatures, and atmospheric composition creates a complex tapestry that defies simple explanations. Yet, it's precisely this complexity that makes neutron stars such fascinating objects to study. With every discovery, we inch closer to unraveling the riddle of their atmospheres, shedding light on the extraordinary physics that govern these cosmic marvels. Now shifting our gaze to the mystery of neutron star birth kicks, we encounter one of the most dynamic and puzzling aspects of these cosmic objects. When a neutron star is born from the explosive death of a massive star, it doesn't just sit quietly in space, it often rockets away at astonishing speeds, sometimes exceeding 1,000 kilometers per second. This phenomenon, known as a birth kick, has left scientists scratching their heads for decades. Why do these newborn neutron stars, which are already incredibly dense and compact, get launched across the galaxy like cosmic cannonballs? One of the leading theories points to the chaotic nature of supernova explosions. When a massive star collapses and explodes, the process is rarely symmetrical. Even a slight imbalance in the explosion can create a powerful recoil effect, propelling the newly formed neutron star in the opposite direction. Imagine a firework bursting unevenly. The force isn't evenly distributed, and the debris flies off in unpredictable directions. In the case of neutron stars, this asymmetry could be enough to give them a significant kick. However, while this explanation makes sense in theory, the exact mechanisms behind these asymmetrical explosions are still poorly understood. Another intriguing possibility involves neutrinos, the ghostly particles that flood out of a collapsing star in enormous numbers. During a supernova, trillions upon trillions of neutrinos are emitted, carrying away a significant portion of the star's energy. Some scientists believe that if these neutrinos are emitted unevenly, they could create a kind of rocket effect, pushing the neutron star in one direction. This neutrino-driven mechanism is a fascinating idea, but it's incredibly difficult to test. Neutrinos are notoriously hard to detect, and the conditions inside a supernova are so extreme that modeling this process accurately remains a major challenge. Adding to the mystery is the fact that not all neutron stars receive the same kind of kick. Some are observed moving relatively slowly, while others are flung across the galaxy at breakneck speeds. This variation suggests that multiple factors might be at play, such as the mass of the original star, the strength of the magnetic fields, or even the presence of a companion star. For example, if a neutron star is born in a binary system, its motion could be influenced by the gravitational pull of its partner, complicating the picture even further. The implications of these birth kicks are profound. A neutron star moving at high speeds can travel vast distances over its lifetime, potentially escaping its home galaxy altogether. This means that some neutron stars we observe today might have originated in entirely different regions of the universe. Understanding the forces behind these kicks could also shed light on the broader processes of stellar evolution and the distribution of matter in the cosmos. Yet, despite decades of research, the exact cause of neutron star birth kicks remains elusive. Each new observation brings us closer to unraveling this mystery, but the interplay of asymmetrical explosions, neutrino emissions, and other factors creates a puzzle that defies simple solutions. As we continue to study these high-speed wanderers, we're reminded once again of the incredible complexity and unpredictability of the universe. And with every discovery, we inch closer to understanding the forces that shape the lives and deaths of stars. Now turning to the strange behavior of accretion-powered pulsars, we find ourselves exploring one of the most fascinating and complex interactions in the cosmos. When a neutron star is part of a binary system, it doesn't just sit idly by, it can pull matter from its companion star, creating a swirling disk of gas and dust around itself. This process, known as accretion, powers some of the most energetic phenomena in the universe, including intense X-ray emissions and the characteristic pulsing behavior of these neutron stars. The accretion process begins when the neutron star's immense gravitational pull strips material from its companion. This material spirals inward, forming what's called an accretion disk. As the matter in the disk gets closer to the neutron star, it heats up to extreme temperatures, emitting X-rays that can be detected across vast distances. But here's where things get really interesting. The neutron star's magnetic field plays a crucial role in shaping how this material behaves. The magnetic field can channel the incoming matter toward the star's magnetic poles, creating hotspots that rotate with the star and produce the pulsar's signature flashes of light. However, the exact mechanics of this process are far from fully understood. For instance, why do some accretion-powered pulsars exhibit erratic behavior, with their X-ray emissions fluctuating unpredictably? Scientists suspect that the dynamics of the accretion disk itself might hold the key. The disk isn't a smooth, uniform structure, it's turbulent and prone to instabilities. Changes in the rate at which material flows into the disk, or even interactions between the disk and the neutron star's magnetic field, could lead to these sudden bursts of activity. But modeling these interactions is incredibly challenging, as it requires accounting for the extreme conditions near the neutron star, where gravity, magnetism, and high-energy physics all come into play. Another unsolved mystery is the role of the neutron star's magnetic field in regulating the accretion process. Some pulsars have incredibly strong magnetic fields, while others have much weaker ones. How does this difference affect the way material is funneled onto the star's surface? And why do some accretion-powered pulsars seem to switch between different modes of behavior, sometimes emitting steady X-rays and other times producing sudden, intense bursts? These questions remain open, and each new observation adds another piece to the puzzle. Adding to the complexity is the fact that the companion star itself can influence the system. If the companion is a massive star, it might blow strong stellar winds that feed the accretion disk. Alternatively, if the companion is a smaller star, the flow of material might be more steady. The interplay between the two stars, combined with the neutron star's magnetic field and the chaotic nature of the accretion disk, creates a system that's both mesmerizing and maddeningly difficult to decipher. The study of accretion-powered pulsars isn't just about understanding these exotic objects, it's also about unraveling the broader processes that govern the universe. By examining how matter behaves under such extreme conditions, scientists can gain insights into everything from the formation of black holes to the behavior of plasma in high-energy environments. Yet, despite decades of research, the strange behavior of these pulsars continues to challenge our understanding, reminding us that even in the vastness of space, there are still mysteries waiting to be solved. Now shifting our focus to the enigmatic world of neutron star interiors, we encounter the mystery of neutron star superfluidity. Deep within the core of these cosmic giants, scientists believe that neutrons may exist in a state known as a superfluid, a bizarre form of matter that flows without any friction. This phenomenon, while sounding like something out of science fiction, has profound implications for how neutron stars behave, from their rotation to their magnetic fields. The idea of superfluidity isn't entirely new. On Earth, certain materials like liquid helium can become superfluid when cooled to extremely low temperatures. In these conditions, the fluid can flow endlessly without losing energy, even climbing up the sides of a container. But in the heart of a neutron star, the conditions are far more extreme. Here, the immense pressure and density create an environment where neutrons might behave in a similar way, forming a superfluid that defies our everyday understanding of physics. One of the most striking effects of neutron star superfluidity is its impact on the star's rotation. As the superfluid neutrons flow without friction, they can move independently of the star's solid crust. This creates a kind of internal tug-of-war where the crust and the core can rotate at slightly different speeds. Over time, this mismatch can lead to sudden changes in the star's spin, such as the glitches we've observed in pulsars. These glitches, where the star's rotation suddenly speeds up, are thought to be caused by the superfluid core transferring angular momentum to the crust in a sudden burst. But the influence of superfluidity doesn't stop there. It also plays a crucial role in shaping the neutron star's magnetic field. The magnetic field of a neutron star is generated by the motion of charged particles within its interior. If the core is superfluid, the way these particles move and interact could be drastically different, potentially leading to changes in the strength and structure of the magnetic field over time. This might explain why some neutron stars, like magnetars, have such incredibly strong fields while others have much weaker ones. Despite the growing evidence for neutron star superfluidity, many questions remain unanswered. For instance, how exactly does the superfluid transition occur under such extreme conditions? What are the precise properties of this superfluid, and how do they vary from one neutron star to another? And perhaps most intriguingly, could there be other exotic states of matter like quark-gluon plasma coexisting with the superfluid in the core? These questions are at the forefront of astrophysical research, and answering them could revolutionize our understanding of matter under the most extreme conditions in the universe. The study of neutron star superfluidity isn't just about solving a cosmic puzzle, it's about pushing the boundaries of our knowledge. By probing the inner workings of these stars, scientists hope to uncover new insights into the fundamental laws of physics, from quantum mechanics to the behavior of matter at densities far beyond anything we can recreate on Earth. Yet, as with so many mysteries of the cosmos, the more we learn, the more questions arise, reminding us that the universe is always ready to surprise us. Now shifting our gaze to the outer layers of these cosmic marvels, we encounter the puzzle of neutron star crusts. These crusts, though only a few kilometers thick, are some of the most extreme and mysterious structures in the universe. Imagine a material so dense that a single teaspoon of it would weigh billions of tons on Earth. This is the reality of neutron star crusts, where matter is compressed to unimaginable densities, creating a rigid and incredibly strong outer shell. The crust of a neutron star is thought to be composed of atomic nuclei arranged in a lattice, surrounded by a sea of free electrons. But unlike the atoms we're familiar with, these nuclei are packed so tightly that they form a crystalline structure, giving the crust its rigidity. Beneath this layer lies the neutron-rich interior, where the pressure is so intense that neutrons dominate, creating a superfluid core. The boundary between the crust and the core is a region of intense scientific interest, as it's here that the star's internal dynamics and magnetic fields are thought to interact in complex ways. One of the biggest challenges in understanding neutron star crusts is modeling their behavior under such extreme conditions. On Earth, we can study materials under high pressure, but the pressures inside a neutron star are millions of times greater than anything we can recreate in a lab. This makes it incredibly difficult to predict how the crust will behave, especially when subjected to forces like starquakes or the immense gravitational pull of the star itself. These events can cause the crust to crack or deform, releasing bursts of energy that we observe as X-ray or gamma-ray emissions. The crust also plays a crucial role in shaping the neutron star's magnetic field. The magnetic field is generated deep within the star, but it's the crust that channels and shapes these fields as they emerge at the surface. The rigid lattice of the crust can trap and amplify magnetic fields, leading to the incredibly strong fields observed in magnetars. At the same time, the crust structure can also influence how the magnetic field evolves over time, potentially explaining why some neutron stars lose their fields much faster than others. But the mysteries of neutron star crusts don't end there. Scientists are still trying to understand how these crusts form in the first place. When a neutron star is born in a supernova explosion, the outer layers cool and solidify, but the exact process by which this happens is still unclear. Additionally, the crust may hold clues to the star's internal composition, including the presence of exotic particles or phases of matter that we've yet to discover. The study of neutron star crusts isn't just about understanding these stars themselves, it's about unlocking the secrets of matter under the most extreme conditions. By probing the structure and behavior of these crusts, scientists hope to gain new insights into the fundamental forces that govern the universe. Yet, as with so many aspects of neutron stars, the more we learn, the more questions arise, reminding us that the cosmos is full of surprises waiting to be uncovered. Now turning to the rhythmic tremors that ripple through these cosmic giants, we delve into the mystery of neutron star oscillations, often referred to as starquakes. These oscillations are like the heartbeat of a neutron star, tiny vibrations that can reveal secrets about what lies beneath their dense, impenetrable surfaces. But despite their potential to unlock the inner workings of these stars, the exact causes and frequencies of these oscillations remain shrouded in mystery. Imagine a neutron star as a colossal bell, ringing with faint tremors that echo through its structure. These oscillations can be triggered by various events, such as the cracking of the star's rigid crust during a starquake or the sudden rearrangement of its magnetic field. When these vibrations occur, they send ripples through the star, causing it to ring at specific frequencies. By studying these frequencies, scientists can infer details about the star's internal composition, such as the density of its core or the properties of its superfluid interior. It's like listening to the sound of a drum to figure out what it's made of. However, the challenge lies in understanding why these oscillations happen in the first place. While starquakes are a leading explanation, the exact mechanisms behind them are still unclear. For instance, what causes the crust to crack? Is it the immense gravitational forces, the buildup of stress from the star's rotation, or something else entirely? And why do some neutron stars oscillate more frequently than others? These questions remain unanswered, leaving scientists to piece together clues from the limited data we have. Adding to the complexity is the fact that neutron star oscillations are incredibly difficult to detect. The vibrations are often faint and short-lived, requiring highly sensitive instruments to capture them. Even when detected, the data can be hard to interpret as the oscillations are influenced by a multitude of factors, including the star's magnetic field, rotation rate, and even its history of collisions or accretion events. This makes it challenging to isolate the specific causes of these oscillations and understand their true nature. Despite these challenges, the study of neutron star oscillations holds immense promise. By unraveling the mysteries of these vibrations, scientists could gain unprecedented insights into the extreme physics at play within neutron stars. For example, oscillations could reveal how matter behaves under the crushing pressures found in the star's core, shedding light on the nature of ultra-dense matter and the fundamental forces that govern it. They could also help us understand how neutron stars evolve over time, from their fiery births in supernova to their eventual fates as dark remnants or black holes. Yet, as with so many aspects of neutron stars, the more we learn, the more questions arise. Each oscillation detected is a piece of a larger puzzle, one that continues to challenge our understanding of these enigmatic objects. And as we listen to the faint echoes of these cosmic bells, we're reminded that the universe is full of mysteries waiting to be uncovered, one vibration at a time. Now shifting our focus to the invisible forces that shape these cosmic powerhouses, we explore the enigma of neutron star magnetic field evolution. These magnetic fields, some of the strongest in the universe, are not static, they change over time, and the reasons behind these changes are as mysterious as the stars themselves. Why do some neutron stars lose their magnetic fields at a rapid pace, while others retain their strength for millions of years? The answer lies in a complex interplay of internal and external forces, each leaving its mark on the star's magnetic fingerprint. At the heart of this mystery is the neutron star's crust, a dense, rigid layer that plays a crucial role in shaping its magnetic field. As the star ages, the crust undergoes subtle shifts and fractures, a process known as crustal dynamics. These movements can alter the magnetic field structure, causing it to weaken or even realign over time. Think of it like a giant magnet buried beneath a shifting landscape. The cracks and movements in the crust can disrupt the field, leading to changes that scientists are still working to fully understand. But the crust isn't the only player in this cosmic drama. Deep within the neutron star's core, exotic processes are at work. The core is thought to contain superfluid neutrons, particles that flow without friction, and their behavior can influence the magnetic field in unexpected ways. For instance, as the superfluid rotates, it can generate currents that either amplify or dampen the star's magnetic field. This interaction between the core and the crust creates a dynamic environment where the magnetic field is constantly evolving, shaped by forces we can only begin to comprehend. External factors also come into play. Neutron stars often exist in binary systems where they interact with a companion star. As material from the companion star falls onto the neutron star, it can alter the star's rotation and, in turn, its magnetic field. This process, known as accretion, can either rejuvenate a fading magnetic field or accelerate its decline, depending on the circumstances. Even collisions with other neutron stars or black holes can leave a lasting impact, reshaping the magnetic field in ways that defy simple explanation. Despite decades of research, the evolution of neutron star magnetic fields remains one of the most puzzling aspects of these cosmic objects. Why do some stars lose their fields so quickly while others maintain their strength for eons? Is it due to differences in their internal structure, their environments, or something else entirely? Each discovery brings us closer to answering these questions, but the full picture remains elusive. What we do know is that understanding magnetic field evolution is key to unraveling the life story of neutron stars. These fields influence everything from the star's rotation to its emissions of X-rays and gamma rays, shaping its behavior over millions of years. By studying how these fields change, scientists can piece together the history of individual stars and gain insights into the broader processes that govern the universe's most extreme objects. As we continue to probe the secrets of neutron star magnetic fields, we're reminded of just how much there is still to learn. Each star is a unique laboratory, offering clues about the fundamental forces that shape our cosmos. And with every new observation, we move one step closer to unlocking the mysteries of these magnetic marvels, one field line at a time. Now turning to one of the most dramatic events in the cosmos, we dive into the mystery of neutron star collisions. When two neutron stars collide, the universe itself seems to hold its breath. These cataclysmic events unleash a cascade of phenomena, from ripples in spacetime known as gravitational waves to blinding bursts of gamma rays and the creation of heavy elements like gold and platinum. Yet, despite the incredible energy and complexity of these collisions, many questions remain unanswered about how they unfold and what they reveal about the nature of matter under extreme conditions. When neutron stars merge, the collision is so violent that it distorts the fabric of spacetime, sending out gravitational waves that can be detected billions of light years away. These waves provide a unique window into the event, allowing scientists to study the dynamics of the collision in unprecedented detail. But what exactly happens during the merger itself? The intense gravitational forces and extreme densities involved create conditions that are impossible to replicate on Earth, making it difficult to fully understand the processes at play. One of the most striking outcomes of a neutron star collision is the gamma ray burst, a flash of high-energy radiation that can outshine an entire galaxy for a brief moment. These bursts are thought to be produced by jets of particles moving at nearly the speed of light, but the exact mechanism behind their formation is still a mystery. Why do some collisions produce such powerful bursts, while others seem to generate little or no gamma-ray emission? The answer may lie in the alignment of the star's magnetic fields or the properties of the material ejected during the collision. Another fascinating aspect of neutron star mergers is their role in creating heavy elements. The intense heat and pressure generated during the collision forge elements like gold, platinum, and uranium in a process known as rapid neutron capture, or the R process. This discovery has revolutionized our understanding of where these elements come from, but many questions remain. For instance, how much of each element is produced in a single collision, and how do these elements spread throughout the universe? The answers could help us piece together the cosmic history of the elements that make up our world. The aftermath of a neutron star collision also raises intriguing questions about the fate of the merged object. In some cases, the collision may result in a new, more massive neutron star, while in others it could collapse into a black hole. What determines the outcome? Is it the mass of the original stars, their rotation, or something else entirely? Understanding this process could shed light on the boundary between neutron stars and black holes, one of the most enigmatic frontiers in astrophysics. As we continue to study neutron-star collisions, each new observation brings us closer to unraveling these cosmic mysteries. From the ripples in space-time to the creation of precious metals, these events are a testament to the incredible forces at work in the universe. And with every discovery, we gain new insights into the nature of matter, the origins of the elements, and the extreme conditions that shape the cosmos. The story of neutron-star collisions is still being written, and each chapter promises to reveal something extraordinary. Now shifting our gaze to another cosmic enigma, we explore the high-speed jets of particles that some neutron stars unleash into the void. These jets, traveling at nearly the speed of light, are among the most powerful and mysterious phenomena in the universe. But what powers these incredible bursts of energy, and why do they behave in such unpredictable ways? The answers lie deep within the extreme physics of neutron stars, where gravity, magnetism, and matter interact in ways we are only beginning to understand. At the heart of a neutron star, the intense gravitational pull and rapid rotation create conditions that can launch jets of particles into space. These jets are often observed in neutron stars that are part of binary systems where they accrete matter from a companion star. As this material spirals toward the neutron star, it heats up and forms a swirling disk. The interaction between the magnetic fields of the neutron star and this accretion disk is thought to be the engine that powers the jets. But the exact mechanism remains unclear. Why do some neutron stars produce jets while others do not, and what determines the direction and intensity of these jets? These are questions that continue to puzzle scientists. One of the most intriguing aspects of neutron star jets is their unpredictability. Unlike the steady beams of light from a lighthouse, these jets can vary dramatically in their intensity and direction. Sometimes they appear to flicker or even shut off entirely, only to reignite with even greater force. This erratic behavior suggests that the processes driving the jets are highly dynamic and sensitive to changes in the neutron star's environment. For example, fluctuations in the rate of accretion or shifts in the star's magnetic field could play a role. But without a complete understanding of these factors, predicting the behavior of neutron star jets remains a formidable challenge. Another layer of mystery surrounds the composition of these jets. While they are primarily made up of electrons and positrons, there may also be heavier particles involved. The exact mix of particles and how they are accelerated to such incredible speeds is still a topic of active research. Some theories suggest that magnetic reconnection, a process where magnetic field lines break and reconnect, could be responsible for accelerating the particles. Others propose that the jets are powered by the rotational energy of the neutron star itself. Each of these ideas offers a piece of the puzzle, but none provide a complete picture. The study of neutron star jets is not just an academic exercise. It has profound implications for our understanding of the universe. These jets can influence their surroundings, heating interstellar gas and even triggering the formation of new stars. They also serve as natural laboratories for testing the laws of physics under extreme conditions. By unraveling the secrets of neutron star jets, we could gain new insights into the nature of matter, energy, and the forces that shape the cosmos. As we continue to observe and analyze these cosmic phenomena, each discovery brings us closer to understanding the forces that drive neutron star jets. From their unpredictable behavior to their role in shaping the universe, these jets are a testament to the incredible complexity and beauty of the cosmos. And with every new observation, we edge closer to solving one of the most fascinating puzzles in astrophysics. Now turning to one of the most fundamental mysteries of neutron stars, we delve into the challenge of measuring their mass and radius. These two properties are not just numbers on a page, they hold the key to understanding the very nature of matter under the most extreme conditions in the universe. But why is it so difficult to pin down these values, and why do they matter so much? The answers lie in the extreme environments of neutron stars, where matter is compressed to densities far beyond anything we can recreate on Earth. Measuring the mass and radius of a neutron star is no simple task. Unlike planets or even ordinary stars, neutron stars are incredibly small and dense, with diameters of only about 20 kilometers but masses up to twice that of our Sun. This means that even the most advanced telescopes struggle to resolve their size directly. Instead, scientists rely on indirect methods, such as observing how neutron stars interact with their surroundings or how they emit X-rays and gravitational waves. Each method comes with its own set of challenges and uncertainties, making it difficult to arrive at precise measurements. One of the most promising techniques involves studying neutron stars in binary systems. When a neutron star orbits another star, the gravitational pull between them can reveal the neutron star's mass. By carefully tracking the orbital motion, scientists can calculate the mass with remarkable accuracy. However, determining the radius is much trickier. For this, researchers often turn to X-ray observations, analyzing the thermal radiation emitted from the neutron star's surface. The shape and intensity of this radiation can provide clues about the star's size, but interpreting the data requires complex models that account for factors like the star's magnetic field and atmosphere. The stakes are high because the mass and radius of a neutron star are directly tied to the equation of state of ultra-dense matter. This equation describes how matter behaves under the crushing pressures found inside neutron stars, where atomic nuclei dissolve into a sea of neutrons and other exotic particles. By measuring the mass and radius of multiple neutron stars, scientists can test different theories about this equation of state, narrowing down the possibilities and revealing the true nature of matter at its most extreme. Recent observations have brought us closer to solving this mystery. For example, gravitational wave detectors like LIGO and Virgo have captured the ripples in spacetime caused by neutron star collisions. These events provide a unique opportunity to measure the masses and radii of the colliding stars, offering new insights into the equation of state. Similarly, X-ray telescopes like NICE mission have made groundbreaking measurements of neutron star radii, challenging some long-held assumptions and opening up new avenues for research. The implications of these discoveries are profound. Understanding the equation of state of ultra-dense matter could revolutionize our knowledge of particle physics, nuclear physics, and even the evolution of the universe itself. It could also help us answer some of the biggest questions in astrophysics, such as what happens when neutron stars collide and whether they can form black holes. Each new measurement brings us closer to unraveling these cosmic secrets, shedding light on the fundamental forces that shape our universe. As we continue to refine our techniques and gather more data, the mystery of neutron star mass and radius remains a tantalizing puzzle. It's a reminder of how much we still have to learn about the cosmos and the incredible potential of science to uncover its deepest secrets. With every new observation, we edge closer to understanding the true nature of matter under the most extreme conditions imaginable. Now shifting our focus to another intriguing puzzle, we explore the enigma of neutron star magnetic field alignment. Why do some neutron stars have magnetic fields that are perfectly aligned with their rotation axes, while others are wildly misaligned? This seemingly simple question has profound implications for how these stars behave, how they emit energy, and even how they evolve over time. At the heart of this mystery is the relationship between a neutron star's magnetic field and its rotation. In many cases, the magnetic field axis and the rotation axis are aligned, meaning they point in the same direction. This alignment is often seen in younger neutron stars where the magnetic field is strong and stable. However, in other cases, the magnetic field axis is tilted, sometimes dramatically, relative to the rotation axis. This misalignment creates a wobbling effect, causing the star's magnetic poles to sweep through space like a cosmic lighthouse. This is what gives rise to the pulsating radio emissions we observe from pulsars. But why do some neutron stars start off misaligned while others remain aligned? One leading theory suggests that the alignment depends on the conditions during the star's formation. If the supernova explosion that creates the neutron star is asymmetric, it could impart a kick to the newborn star, causing its rotation axis to tilt relative to its magnetic field. Alternatively, interactions with a companion star in a binary system could also play a role, gradually altering the alignment over time. The implications of magnetic field alignment are far-reaching. For pulsars, the angle between the magnetic field and the rotation axis determines the strength and pattern of their emissions. A misaligned field can produce more complex and variable signals, making these pulsars harder to study but also more fascinating. Over time, the magnetic field of a neutron star can evolve, sometimes becoming more aligned or even more tilted, depending on the star's internal dynamics and external environment. This evolution has significant consequences for the star's lifespan. A misaligned magnetic field can cause the neutron star to lose rotational energy more quickly, slowing its spin and potentially shortening its active phase as a pulsar. On the other hand, an aligned field might allow the star to maintain its rotation for longer, extending its life as a visible source of radiation. Understanding these processes is crucial for piecing together the life cycle of neutron stars and predicting their behavior over billions of years. Recent observations have added new layers to this mystery. For example, some neutron stars exhibit sudden changes in their alignment, known as spin axis reorientation events. These events, which can happen over relatively short timescales, suggest that the internal structure of neutron stars is far more dynamic than previously thought. Additionally, studies of neutron stars in binary systems have revealed how interactions with a companion can influence magnetic field alignment, providing valuable clues about the forces at play. The enigma of neutron star magnetic field alignment is more than just a curiosity. It's a window into the complex interplay of forces that govern these extreme objects. By unraveling this mystery, we can gain deeper insights into the physics of pulsars, the evolution of neutron stars, and the fundamental nature of magnetic fields in the universe. As we continue to observe and study these cosmic wonders, each discovery brings us closer to understanding the intricate dance of rotation, magnetism, and time that defines the life of a neutron star. Now turning to one of the most tantalizing mysteries in astrophysics, we delve into the possibility of neutron stars interacting with dark matter. Could these dense stellar remnants be capturing elusive dark matter particles? And if so, what would that mean for our understanding of the universe? This question sits at the intersection of two of the greatest cosmic puzzles, neutron stars and dark matter, and the answers could reshape our knowledge of both. Dark matter, which makes up about 85% of the universe's mass, remains invisible to us because it doesn't emit, absorb, or reflect light. Yet, its gravitational effects are undeniable, influencing the motion of galaxies and the large-scale structure of the cosmos. Neutron stars, with their incredibly strong gravitational fields, might be the perfect laboratories to detect dark matter. The idea is that as dark matter particles pass through a neutron star, they could be captured by its gravity, accumulating over time and potentially altering the star's properties in observable ways. One proposed effect is that dark matter could cause neutron stars to cool faster than expected. Normally, neutron stars cool by emitting neutrinos, but if dark matter particles interact with the star's core, they could carry away additional energy, accelerating the cooling process. This would leave a detectable signature in the star's temperature and radiation output. Another possibility is that dark matter could affect the star's rotation. If enough dark matter accumulates, it could slow down the star's spin or even cause subtle changes in its pulsar emissions. However, detecting these interactions is no easy task. Neutron stars are already complex objects, and teasing out the subtle effects of dark matter requires incredibly precise measurements. Current telescopes and instruments may not yet be sensitive enough to distinguish dark matter-induced changes from other natural variations in neutron star behavior. Additionally, the nature of dark matter itself is still poorly understood. We don't know exactly how dark matter particles interact with ordinary matter, if at all, which makes it difficult to predict what signatures to look for. Despite these challenges, the potential rewards are immense. If neutron stars are indeed capturing dark matter, they could provide the first direct evidence of its existence and properties. This would be a monumental breakthrough, offering clues about the composition of dark matter, its interaction with normal matter, and its role in the evolution of the universe. It could also help explain why dark matter has remained so elusive, shedding light on one of the most profound mysteries in modern science. As researchers continue to refine their models and develop more advanced observational tools, the search for dark matter in neutron stars remains a vibrant area of study. Each new observation brings us closer to uncovering the secrets of dark matter and its potential connection to these enigmatic stellar objects. The mystery of neutron star dark matter interactions is not just a scientific challenge, it's a gateway to understanding the hidden forces that shape our universe. Now shifting our gaze to an even more extraordinary cosmic phenomenon, we explore the rare and puzzling existence of planets orbiting neutron stars. These neutron star exoplanets, as they're called, are among the most extreme and enigmatic worlds in the universe. How do planets form and survive in the harsh environment around a neutron star? And what does their existence tell us about the resilience and adaptability of planetary systems? Neutron stars are the remnants of massive stars that have exploded in supernova, leaving behind an ultra-dense core with a gravitational pull so strong that it warps space and time. The idea that planets could exist in such an environment seems almost impossible, yet astronomers have discovered a handful of these bizarre worlds. One of the most famous examples is the planetary system around the pulsar FRB 1257+12, which hosts at least 3 planets. These planets are thought to have formed from the debris left behind after the supernova explosion, or perhaps they were captured from a passing star. Either way, their survival in such a hostile environment is nothing short of miraculous. The conditions around a neutron star are extreme by any measure. The star's intense magnetic fields, powerful radiation, and frequent bursts of X-rays and gamma rays would vaporize most planets in an instant. Yet somehow, these neutron star exoplanets endure. One theory suggests that they might be made of incredibly dense materials, like iron or even exotic forms of matter, allowing them to withstand the intense radiation and gravitational forces. Another possibility is that they formed much farther away from the neutron star and migrated inward over time, somehow avoiding destruction. The existence of these planets challenges our understanding of how planetary systems form and evolve. Traditional models of planet formation are based on the relatively calm environments around young stars, where dust and gas slowly clump together to form planets. But around a neutron star, the process would have to be far more chaotic and rapid, with planets forming from the ashes of a cataclysmic explosion. This raises fascinating questions about the diversity of planetary systems in the universe and the potential for life in even the most extreme environments. Studying neutron star exoplanets also provides a unique opportunity to test the limits of planetary science. By observing how these planets interact with their neutron star hosts, astronomers can learn more about the properties of ultra-dense matter, the effects of extreme radiation, and the dynamics of highly energetic systems. Each discovery adds a new piece to the puzzle, helping us understand not only these exotic worlds but also the broader processes that shape planetary systems across the cosmos. As we continue to search for more neutron star exoplanets, each new finding pushes the boundaries of what we thought was possible. These worlds remind us that the universe is full of surprises, and that even in the most hostile environments, the seeds of new worlds can take root. The puzzle of neutron star exoplanets is a testament to the resilience of matter and the endless creativity of the cosmos, inviting us to rethink our assumptions and explore the unknown. Now turning to the final chapter in the life of a neutron star, we delve into the mystery of their ultimate fate. What happens to these cosmic remnants as they age? Do they collapse into black holes, cool into dark, silent remnants, or transform into something entirely unexpected? The life cycle of a neutron star is one of the most intriguing puzzles in astrophysics, and it raises profound questions about the nature of matter, gravity, and the universe itself. Neutron stars are born in the fiery aftermath of supernova explosions, but their journey doesn't end there. Over billions of years, these ultra-dense objects continue to evolve, shaped by both their internal processes and external influences. One possibility is that a neutron star could eventually collapse into a black hole. This might happen if it gains too much mass, either through accretion from a companion star or through a collision with another neutron star. But what determines the tipping point? Why do some neutron stars cross this threshold while others remain stable? These are questions that still baffle scientists. Another possibility is that neutron stars simply cool down over time, fading into dark, cold remnants known as black dwarfs. As they lose their heat and energy, their magnetic fields weaken, and their once powerful emissions fade into silence. But this process is incredibly slow, taking trillions of years, far longer than the current age of the universe. Could there be neutron stars out there that have already reached this stage? Or do other forces intervene before they can cool completely? External factors like accretion and collisions also play a crucial role in shaping the fate of neutron stars. When a neutron star pulls in material from a nearby star, the added mass can trigger dramatic changes, from sudden bursts of X-rays to the formation of powerful jets. Collisions between neutron stars, on the other hand, can produce some of the most energetic events in the universe, including gravitational waves and gamma-ray bursts. But what happens to the neutron stars after such a collision? Do they merge to form a black hole, or could they create a new, even more exotic object? The long-term evolution of neutron stars is a mystery that challenges our understanding of physics. Current models struggle to predict how these objects will behave over cosmic timescales, and observations are limited by the fact that neutron stars are incredibly difficult to detect once they cool and fade. Each new discovery, from gravitational wave detections to observations of pulsar glitches, adds a piece to the puzzle, but the full picture remains elusive. As we ponder the ultimate fate of neutron stars, we're reminded of the vastness and complexity of the universe. These enigmatic objects, born from the ashes of dying stars, continue to evolve in ways we're only beginning to understand. Their life cycles challenge us to rethink our assumptions about matter, energy, and the forces that shape the cosmos. And as we uncover more about their secrets, we come closer to answering some of the biggest questions in science. What happens when a star dies but refuses to fade away? The answer lies in the mystery of neutron star life cycles, a story that is still being written in the stars. As we bring our journey through the mysteries of neutron stars to a close, it's clear that these cosmic enigmas hold the keys to some of the most profound questions in science. From the fleeting brilliance of fast radio bursts to the slow, silent cooling of ancient remnants, neutron stars challenge our understanding of the universe in ways no other objects can. Each mystery we've explored, whether it's the strange behavior of pulsar glitches, the extreme magnetic fields of magnetars, or the elusive nature of quark stars, reveals just how much we still have to learn about the cosmos. These unsolved puzzles aren't just academic curiosities. They push the boundaries of physics, forcing us to rethink the fundamental laws that govern matter, energy, and gravity. They remind us that the universe is far more complex and wondrous than we often imagine. And as we continue to study neutron stars, we're not just uncovering the secrets of these distant objects, we're also gaining insights into the very fabric of reality itself. But the story of neutron stars is far from over. With every new discovery, from gravitational wave detections to observations of neutron star collisions, we're piecing together a clearer picture of these extraordinary objects. And yet, for every question we answer, new mysteries emerge, keeping scientists and all of us on the edge of our seats. So, what do you think about these cosmic puzzles? Which mystery of neutron stars fascinates you the most? Let us know in the comments below. We'd love to hear your thoughts. And if you enjoyed this deep dive into the wonders of space, don't forget to hit that like button, subscribe to our channel, and ring the notification bell so you never miss an update. The universe is full of mysteries waiting to be uncovered, and we're just getting started. Stay curious, keep exploring, and remember, the stars have stories to tell, and we're here to listen. Until next time, keep looking up.